So this video is actually the fourth and fifth lessons for Chapter 7 for electricity and magnetism. The two lessons basically go together. It's probably easy just to put them all into one video here. We're going to look at some applications of what you've seen so far over the last couple of lessons. Applications of the force on a charge, QVB, and the force on a current carrying wire, LIB. As we've done before, let's just take a second and review what we've seen so far. Permanent magnets have north ends and south ends, and magnetic field comes out of the north end and wraps its way around to the south end. If you ever want to know which way the magnetic field is pointing, just grab a compass and take a look, and it will actually point in the direction of magnetic field. So that's a handy way to figure out which way the magnetic field's going. We saw two different ways that you can make magnetic field with currents. There's the long straight wire. Doesn't work very well, but it's still good to know how that direction works by doing that grab with your fist around the wire, and then the solenoids, which works way better. And over the last couple of classes, we looked at these two ways you could create force. QVB on a single charge moving in a magnetic field. We're going to look at applications of that right off the start. And then F equals LIB, the force on a wire, and we'll look at some applications of that near the end of this video. So just a few different little applications here where you can see how these forces can actually be used in real life. So let's start off with taking a look at some good old classic, what we call cathode ray tube televisions, or CRT televisions. You don't see very many of these anymore. They've got the big glass screen up front with some paint on the back side that when electrons strike the paint, it actually glows. And there's an electron gun, or even sometimes three guns in the back that shoot electrons towards the screen in order to make that paint glow. And even though we don't see these TVs anymore, it's kind of a neat little application of how you can use magnetic fields to steer the electron beam. So here's a cutaway of an old school television, and back here is the electron gun, and there are a couple of parallel plates. I've kind of symbolized them here. One plate's got a hole, so the electrons can be shot out, and we're going to accelerate electrons at this end, but then we need to steer them kind of like an Etch-a-Sketch, so you can get them to land anywhere you want on the screen on the back side where the paint is. And I've suggested to you before in Chapter 5 that you could use electric fields to steer the beam around, F equals QE for that. But it turns out for these old school televisions, they most often used magnetic fields to do that. So yes, indeed, on the left side, you've got the accelerating plates. We'll use electric fields to get the electrons going. But then in order to make them strike the screen in an interesting place, what we can do is put in some magnetic field somewhere around here on the television in order to steer the beam. But there is a weird cross product that goes on in there, so you have to be very careful about the direction of the magnetic field. Imagine these little rings here are actually some solenoids, and they're creating a magnetic field that's coming at us, kind of a 3D picture. So you've got B field coming towards you out of the page, and you've got the electrons, they're negative, heading towards your right. So if I was doing QVB, I'd have my thumb pointing to my right, and I'd have my magnetic field coming out of my page. And my right hand at that point, it's kind of awkward to get into that position, but my right hand has its force finger pointing down. And if they were positively charged, these charges would actually get deflected downward and strike the screen down here somewhere. But they are electrons, so they're going to end up bending upwards. If you wanted the electrons to strike the screen down here to make it glow down there, just reverse the direction of this magnetic field. And if you wanted the electrons to kind of come at us a little bit and strike the screen closer to us or farther away, then you'd actually make a magnetic field that was in the vertical orientation over here in order to have those electrons either go into the page or out of the page. So it's just there's no math to that. Just a neat little application of F equals QVB, where they actually did use magnetic fields inside those old school televisions in order to steer the beam around. Next thing. Something called velocity selectors. Okay, this is something that you can actually do some calculations for. Probably be expected to do some of these calculations at the end of the chapter, so you might want to pay a little more attention to this part. For velocity selectors, they're very important if you were, say, working at a particle accelerator and you're accelerating particles and not all of the particles are traveling at the same speed. So here's actually a picture of one of the beam lines at Triumph. It's our particle accelerator in Vancouver. I believe this particular beam line is what they call M15. Where they do some work called mu-SR, and they actually use muons to probe into the heart of matter. And it's important when you're actually running these beams of particles that you make sure that their speeds are exactly what you want. And sometimes the particles coming down the pipe right here will actually have a slight variance in their speed. Some will be a little faster, a little slower than others. And so you need a device in there that will actually eliminate particles that don't have the right speed. Don't let them go by, but only let ones go by that have the perfect speed. And there is a neat, simple way to do that with two different fields, a magnetic field and an electric field that will actually be crossed with each other. So the picture for that, you've already got these black lines, I think, on your note package. What we're going to do is make those some parallel plates, some cookie sheets, and we'll make the top one perhaps positive and the bottom one negative. That's going to create an electric field in there, but let's draw that in. It'll go from the top to the bottom. I'm going to leave a little room right here so I can draw some more stuff. But the electric field would be a warning about force, saying, hey, watch out. If there's any positive charges in there, they're going to get shoved towards the bottom plate. And that's great. But in addition to having that electric field pointing down towards the bottom of your note page, I'm also going to have a magnetic field perpendicular to that. Let's have it going into the page. That's what those X's represent. And so here comes a beam of particles, and I only want this beam of particles, which we'll say is positive, I only want it to get through if it has the perfect speed. If it's too fast or too slow, I want to filter it out. I want to make it kind of take a turn so it doesn't keep on going to the far right side of your note page. Now there's going to be a force magnetically in that direction. You can do that with the right hand rule. You'd have on your right hand your thumb pointing to the right and your pointing finger, your magnetic field, going into the page, and you'd see that your force finger, your middle finger, does point upwards. So there's a magnetic force that goes that way, but there's also the electric force, the QE force, going down. Now what's interesting is the QE, the electric force, does not depend on speed, but the magnetic force does. So depending on whether or not the speed is just right, you will or you won't get a balance between those forces. At just the perfect speed, then you're going to find these forces are equal and the particle will go through undeflected. At the wrong speed, it will either get bent up and out of the way or down and out of the way, and it won't continue on to the experiment. So all we have to do to find this math relationship here is just equate those two forces, the QE and the QVB force. It doesn't even matter how big the Q is. For that matter, it doesn't even matter if it's positive or negative. It would just reverse the direction of those arrows, but they would still be in a perfect balance when the electric field was equal to the velocity times the magnetic field. So as a researcher, you would set up an electric and a magnetic field to be just the right size to allow through the velocity that you were looking for. So as long as that E, measured in newtons per coulomb, and the B, measured in Tesla, had that right quotient, you'd have the right velocity coming through. And so it's just a handy way at a particle accelerator to actually pick out just the right speed. Now, speaking of particle accelerators, let's take a look at how the place down in Vancouver actually launches those particles very, very fast. It's called a cyclotron, and the key thing that we're going to look at for Physics 12 is how you can use magnetic fields in a cyclotron to keep those particles contained in one room, in one area, where you can slowly, well, not slowly, where you can take some time to spin them up to speed. And so you can use magnetic fields to hold them in a nice little circle. So I think already on your page you have this. Imagine you've got a positive charge that's circulating around in this magnetic field. Now actually at Triumph you can go for a tour there and they will correctly point out that originally they actually accelerate negative charges and then they remove the electrons later to make it positive. But let's just say that it's positive and it's going to end up going in a circle because of that QVB force. If you take your thumb and point it to the right and you're pointing magnetic field into the page, you'll see that your force finger does point towards the middle of that circle. So it'll just sit there and beautifully circulate just around and around and around. And that'll give us some time to maybe apply some electric fields to it to give it a little push to make it go faster, but at least we'll have a way to contain it. Now for Physics 12, this is the extent of the calculations that we're going to look at. You know, what happens with the math for the circular motion? Well, we've got for the net force, QVB. After all, today is the application of QVB and LIV. Don't even worry about gravity. It's too small to be an issue. The QVB force is much bigger. And we're going to equate that to the mass times the acceleration, v squared divided by r for circular motion. It fits beautifully with our second unit for Physics 12. Most people at this point like to reduce the V's. You don't need one of those V's on each side. You can reduce, and then while you're at it, you might as well move the R to the other side. And this actually is what's sometimes called the cyclotron equation. It's kind of interesting, the relationship here. Over on the right-hand side, you have the momentum of the particle. And what I'm seeing is for a given magnetic field and charge, once that charge is in that room with magnetic field, if you make it go faster and faster, if you increase the momentum of the particle, then you will increase the radius of the particle. So the radius is actually proportional to the momentum. So they actually start off in the middle of the room at Triumph, and they spin them around in small little circles at lower speeds. And then while they're giving them little pushes with electric fields, what we notice is their circular ring that they're following, their circular path they're following actually grows until it's so big we can't fit it in the room anymore, and then it's time to actually send it out down the beam pipe down towards some sort of target. But a key thing here is how the radius is proportional to the momentum. And obviously with those 5 variables, you could find any one if you were given the other 4. Now, that's kind of the end of where that particular topic is supposed to stop for Physics 12, but I want to show you a couple more things. Since this cyclotron is sitting in our backyard, so to speak, and you can go and tour it, and I encourage you to try that out. Let's just look at some pictures from there. So the cyclotron motion, that's the key thing for Physics 12, but now let's just go for a little joyride here and take a look at some pictures. In general, at a cyclotron, you've got 2 electromagnets to make a magnetic field. And down at Triumph, they're actually in a room about twice the size of our gym. And in that space between the electromagnets is where the particles are going to circulate. And they actually have them go into, well, in this picture here, this is a little bit old school, has them go into these metal little pockets, like little pita pockets. They don't quite do it that way anymore, but it's similar to that. And these metal little pita pockets can be charged, one positive, one negative, and that will create an electric field in here. And as they pass between that gap, it'll actually give them a little kick. Now, when they go back around, you want to make sure you keep kicking them the right way. So we have to keep reversing which of those little pita pockets is positive. And that actually requires quite a bit of radio frequency energy. But let's go and take a look at more pictures here. So this is a very, very small cyclotron. This is not Triumph. This is a small cyclotron. Here are the little pita pockets, so to speak. They're actually called Ds because they look like Ds. And this brass area here is what we call the tank. And there would be a lid on this, and then all of the air would be pumped out. And the charged particles would spin around in here until they're ready to leave, and then they would go out of the tank. And that whole tank would then slide between 2 electromagnets, kind of like what you see in this picture here. But this is way too small to be Triumph. So let's take a look at how big Triumph is. This is Lawrence. He's one of the inventors of the cyclotron, and in his hand he has the original tank that he built for his cyclotron. That fits in his hand for the original one. Here is the size of the tank at Triumph, and you can see people down here getting this thing ready during construction to be lowered into position. So quite a bit larger than the tank that fits into this scientist's hand. That tank actually sits on top of this electromagnet. It's in the shape of a cool little pinwheel. It's actually the Triumph logo now. And then another magnet that looks just like it sits on top. And that's all inside this room that's absolutely massive called the vault. And it's pretty cool. You can go down and tour that. You get a chance to look inside the control room at Triumph too. So if you get a moment, it's a cool thing to do. And that kind of marks the first half of the lesson. That's applications of QVB. Now let's take a look at some applications of LIB, of the force on a wire with some current in it. I want to take a little look at electric motors. Here's like a little $2 motor that inside it has a little rotating part that we can use physics to apply some forces to make it spin. It's got some wire coils in there, and then an electrical connector called a commutator that we can use to send currents into those coils while that whole device called the armature is spinning. This is the picture that's in your notes, and we're going to add a couple of things to it, as you can see. But before we do, let's see if I can get a little video to run here. It may or may not run very well. But here is a little animation of a motor. The yellow part can spin, and it's going to have some current on it from this battery. And when that current is sitting inside this magnetic field, it creates forces on it. And so that, when it runs, looks like this. The current in the yellow wire feels a force because it's in that red magnetic field, and you can see the force is there in green. This little connection here needs to be able to apply electricity while it's spinning, which is kind of neat. Okay, so that's actually this area here called the commutator. And these little spinnable connections are called the brushes that brush up against the commutator. Okay, well, let's kind of tear this thing apart. First thing, you need some magnets. Sometimes people use electromagnets. Here I've got a couple of permanent magnets, and we're going to, inside that, put a little rotating coil. This one has a single loop only just to make it clear and simple, but normally you'd have many wraps of wire because every wrap is going to give you some more torque. So that could be called the coil, or you can call it the armature. Either is fine. And it's going to be bathed in this magnetic field. Now we need to get some electricity, so let's connect it up to a battery with that little rotating connection. So the rotating connection is called a commutator. This particular design is called a split ring because it's two halves of a ring. And these little parts here that I've drawn as little rectangles brush up against it with a little spring pushing them gently to create an electrical connection, but not a lot of friction. And so we have some current flowing here out of the positive end of the battery and along this wire and then back along that one. And now you can do LIB. You can point your thumb in the direction perhaps of this current here. So your thumb kind of goes into the page while your pointing magnetic field finger goes to your right. And you can see that your force finger, your middle finger, points down. And so that's going to create a force downward, an LIB force over on this side of the coil. And there's a corresponding one over here on this side. And together that makes a beautiful twisting torque trying to make this motor rotate nicely. Now for physics 12, we're kind of just supposed to stop there and go, yeah, it'll spin. You know, put some current on that and there'll be these corresponding forces, these complementary forces to create some torque. I just want to give you a peek at the equation for how much torque it creates. It's not part of the course anymore. It used to be, but it was taken out. But I just want to talk about how much this equation actually makes sense. But it's nothing that you're going to see on any test. The amount of torque, measured in Newton meters, is proportional to these four things. The number of wraps, so this one only has one coil, but normally you'd have many of them. The area of the coil, so making the coil bigger in either direction actually helps out. The current in the coil, yeah, that makes sense. And the strength of the magnetic field. So if you can make those four values very large, you can create a really high torque motor. And that's just a neat little application of LIB. Now, we don't need to know about that equation, so we can just look at it and go, yeah, that LIB definitely is what makes those motors run. And that's just kind of a qualitative thing we were going to look at here. Last thing, rail guns. This is a possible device for actually launching satellites into orbit. It's very expensive to launch satellites into orbit, so if you could maybe shoot them up into orbit, that might actually be very beneficial in terms of just, energy. And in a simplified sense, it starts off with two rails. We're going to bolt those rails down so they don't go anywhere because they're going to be exposed to some magnetic field here. So I've got magnetic field going into the page, a whole bunch of it, and these rails connected to a really big voltage source. And then I'm going to lie a little metal device just from rail to rail. And that metal device can slide along those rails. Maybe not a huge amount of friction, but enough contact to make electrical contact. So some current's going to flow from this power supply along the rails and then down along that metal bar. And that metal bar is now a current carrying wire inside a magnetic field. So if you take your thumb and point it to the bottom of the page, and your pointing magnetic field finger pointing into the page, you'll see that your force finger points off to your right. So there would be a nice big LIB force on it pushing this way. And that's going to accelerate it. And as long as it's in contact with those rails, it's going to continue to accelerate. So you could go and figure out exactly how much acceleration you're going to get just based on this force. Now, something to be aware of is, which actual length should you use? Would you use the 2 meters from rail to rail or the 5 meters here? Well, I'd use the 2 because this overhanging section of the yellow bar doesn't have any current on it. And this section also wouldn't have any current on it. So if you're wondering what length would you use in that picture, I'd use the 2. You can calculate that current just with Ohm's law. If you knew how much voltage you had available, what the resistance of the whole circuit was, that's pretty easy to calculate. Acceleration would just be that force, LIB, divided by the mass of that little bar. So you could do this all algebraically if you wanted to. You could say, oh yeah, the acceleration is LIB divided by the m. Now you could subtract friction from that LIB if you needed to, but if there's no friction, that would be great. And if you're wondering, well, what would my final velocity be? Well, take your initial velocity, add on acceleration times time. So there's kind of a way of looking at it with no real numbers at all, just nothing but just symbols, just kind of looking at the relationships there. And like I said, if you wanted to include friction, just subtract that from the LIB. And so those are just 5 little applications of QVB and LIB that finish up now this first half of electricity and magnetism.